Okay. Uh, Today's topic we'll be discussing on strain gauge. On the last 2 days, we have discussed about the different types of resistive sensors like RTD, thermistors, potentiometers, where depending upon the input parameter variable there, uh, maybe temperature, maybe level, maybe other things there, the resistance changes. So we will now take up another type of very popular resistive type sensor, which is called the strain gauge. So from the name itself, it is obvious that it measures the strain. That means it converts the strain into the change in resistance. So basically, if we look at it, it measures strain, or it can measure pressure, or it can measure force, and these all the things, they are convert to the change in resistance, that is the delta R, that is the change in resistance there. And the basic relationship we can say in the linear relationship, that is the delta R by R, that is the change in resistance, is expressed as G into epsilon, where epsilon is the strain and G we call it as gauge factor. We will come to it, what is gauge factor afterwards. So, that is the delta R by R is dependent on, is related with the epsilon by this expression. It is delta R by R into G into is equal to G into epsilon. Now, let us try to find out how does it measure strain, or what is the G, try to evaluate also what is the, how the change in resistance is related with the strain there. Let us try to find out there. For this, we just take up a simple case of to understand the change in resistance due to strain. We take up the simple case, that is a long wire. This is a long wire, say suppose, and this is having a length of capital N. Now, if it is subjected to a force F, some force F there, so what will happen? The length of the long wire will increase, and it is basically at the same time, because the volume has to remain constant. So what will become? It will happen that the long wire will become thinner, and it is it's a change in length, we say, call it, say it is delta L, and obviously the cross sectional area A will change by a amount of delta A. Obviously, if the L increases, delta A decreases. And we know the basic relationship of a resistance is equal to R is equal to rho in L into A, where rho is the resistivity. And obviously, L is the length, and A, capital A, is the area of cross section. So what we can say is that from this expression we can write delta R is equal to del R by del L into delta L plus of del R by del A into delta A plus of del R by del rho into delta rho. So we can say that all the parameters may change, L, A and rho, and in that way that this will be the relationship. And from the relationship, what is del R by del L? We know this is simply, it is rho by A. And what is del R by del A? We can say that this is your, just take the differentiation. So, it would be minus of rho L divided by A square into delta A plus of what is del R by del rho? It is L by A into it is delta rho. Or we can say that this is equal to, I just take out the L common here. If we take out the L common here, or or rather we put it in this way, that we just put yeah, if we can write it in this way, that R into delta L by L, because I just multiply L here and L at the denominator, del R by delta L by L, minus, here it is already R term is there. So, what we will have is that delta A by A plus of what we can say it is R, we take it to a delta rho by rho. Now again, if we assuming circular cross section, if we assume circular cross section, we know that this is equal to A is equal to pi by 4 into d square, where d is the diameter of the wear there. So, what we can say in the same way, we can say it is delta A is equal to this one, del A by del D is nothing but it is pi by 2 into D into delta D. So, basically del A by del D is nothing but pi by 4 into 2D. So, pi by 2 into D into delta D. So, what we can write in that way is that so delta A divided by A is equal to pi by 2 into d into delta D divided by pi by 4 into d square. So, we have it is equal to 2 into delta D by D. So, we have it 2 into delta D by D. So, we can write it down is equal to delta R by R is equal to delta L by L minus of 2 into delta D by D plus of what we can say delta rho by rho. So, this is your expression there. Now, one more thing is important, that the change in length and change in diameter is related, and we define, and this relationship is expressed in terms of, we call it a Poisson's ratio. So, what is a Poisson's ratio? We express it in terms of, it is mu is equal to minus of lateral strain by longitudinal strain. So here it is, we can say it is minus of delta d by d divided by delta L by L. So this is a property of the material of the wire or whatever we are using, the resistive element here we are using in this case, and this is constant for that one. And for most metals, we know that mu is equal to 0.3. We can take it as is equal to 0.3. So in that case, we can have it from this one, this relationship. It is delta R by R is equal to, what is it? It is, I can write it down as delta L by L into 1, and here it is plus of 2 mu plus of delta rho by rho divided by delta L by L. So this is the relationship, as we have told, that delta R by R is equal to delta L by L into 1 plus 2 mu plus delta rho by rho divided by delta L by L. So from this one itself we can say that our relationship delta R by R is equal to delta, we just expressed it in this way, that is equal to G into epsilon. We just say that this can be expressed in this way, and this is equal to, so how do you define this one? The G is defined as gauge factor, which is equal to delta R by R divided by delta L by L is equal to 1 plus 2 mu plus of what we have? It is delta rho by rho divided by delta L by L. So this is a constant, and these are all depends upon, so mu is constant for a particular material, and basically this part, that is delta rho by rho divided by delta L by L, it is basically, it indicates the change in resistivity. Rho is the resistivity, change in resistivity with strain. And this is due to basically what we call it a piezo resistive effect. So it is the due to the strain applied, the resistivity changes, and this is called the piezo-resistive effect. But that also, that what will be that delta rho by rho divided by delta L by L, this is also dependent upon the metallic or the property of the material. So we conclude the gauge factor, which is basically defined as this one, G is equal to delta R by R divided by delta L by L, is denoted by 1 plus 2 mu plus of delta rho by rho divided by delta L by L, and this is basically a material property. It is not dependent upon the it is not dependent upon the length or construction or any other things there. So, one more thing is that, as I have told you, the for most metal, the mu is around 0.3. So, the range of gauge factor, you can say that the first two terms is equal to this 1 plus 2 mu, and these two terms 1 plus 2 mu, this comes to be is equal to 1.6. So, naturally, the rest whatever be the value of the gauge factor for a material, what we can say, for a material metals, we don't have much to play. It depends upon the resistivity, how the resistivity changes. But for metals, the resistivity change is rather insignificant. So, we will see that the gauge factor variation is rather small there. So, you can say that, so this is constant for a particular material, and we can have the gauge factors for different materials or the strain gauge which are commonly used for strain gauge, which are commonly used for strain gauges. So, the commercially available the strain gauges are mostly what we call them, they are the alloys there, particular alloys there. Some of the materials are which is called advance, which is an alloy of 50% copper and 45% nickel. It is gauge factor is, in short we call it GF, is varies between 2.0 to 2.2 there. Next is nichrome. It is 80% nickel and 20% chromium, and gauge factor is varies between 2.2 to 2.5. Then it is isoelastic. Of course, it is a commercial one, and it does not, it's a trade name, so it does not disclose what is the composition. But here we can have a gauge factor, it is around say 3.5. And another one is also karma. These two are the commercial names, trade names, and here we have a gauge factor is around 2.4. So, obviously, there are two things supposed to be remembered. We will come to those things afterwards, that delta air R by R is equal to G into epsilon. So, the change in what could be the changes? So, most of the metallic strain gauges are the gauge factor varying between 2 to 3 or like this. Hardly we can, many of the cases we can assume that it is 2 there. So, if your epsilon is equal to say 10 to the power minus 3, that is normal, the strain we have it is around 1000 microstrain or 10 to the power minus 3. This is around in that range. So, if your gauge factor is equal to 2.0, so what we have is change in resistance delta R by R is equal to 2 into 10 to the power minus 3. So, naturally what will happen in percentage, the change in resistance is very small, around say 0.2 percentage. So, it is 0.2 percentage, and so naturally the change in resistance is small, the change in variation of resistance is small in these cases. So, it could not, so basically for small strain measurement, it may be very difficult or like this. And but the question, but we may require also some other cases or some other types of strain gauge which have got a higher gauge factor, or rather the higher sensitivity. So, we can measure the very low pressure. For example, I would say that, say, suppose our blood pressure measurement. Sometimes we have the blood pressure variation is very small in our fingertip. Sometimes we measure the blood pressure here. So you can easily understand the fluctuations of your blood pressure is very small there. So in that case, this sort of metallic strain gauges may not be very suitable there. So we require another type of materials which we should have a large gauge factor. In fact, you can see that our option is limited because 1 plus mu we cannot have much play there. But what we can do is that the only thing is that where the change in resistivity is high, we choose a material where the change in resistivity due to strain is high, and that we come up and come across, and we can use this one, what we call it a semiconductor type strain gauge. And here the gauge factor varies between 100 to 150. So naturally it is much higher compared to our metallic strain gauges or like this, where we can have it, and basically the semiconductor type strain gauges are used, but so it is much more sensitive, but at the same time the disadvantage is your nonlinearity. So what we will have is that the semiconductor type strain gauges also, we will just discuss this one and see the characteristics. But before that one, let me tell you one more thing there. The question may be that why we choose this sort of strain gauge materials only. Because any metal or anything we could use it, the constraint is that it should have normally the change in resistance or the resistance value. The commercially, we just normally have a commercial strain gauges. They are available in I mean, the available are 120. There are certain standard value: 120 ohm, 350 ohm, 1000 ohm, etc. So we cannot go to the market and say that, okay, I require a strain gauge of say 180 ohm there. See, there are certain, because of the ease in manufacturing of the standard practice of like this, they make it that the strain gauges are like this, in this way: 100 ohm, 120 ohm, sorry, 120 ohm, 350 ohm, 1000 ohm. So to make the strain gauge value resistance high, so And at the same time, the strain gauge size to be very low, we require, number one is that the thickness of the wire should be very small, so that if the thickness is that small, so we can get a larger resistance there. Another thing is also there, that it should be, this material should be very stable. With time, it should not, resistance should not change. So that's why these are the standard practice of purchase, of the strain gauges. Not much deviations are there for the metallic type of strain gauges, but this semiconductor material type of strain gauge is another type of strain gauge, where you can have, you use the semiconductor type materials. And so naturally, once we say semiconductor type material, it could be two types of doping. We can have a N-doped and P-doped. So naturally, we can have a strain gauge of P-type and N-type. So we can have a semiconductor type strain gauge. We can have is that one is a P-type, one is a N-type. So these two types we can have it, and obviously it depends upon the doping there. And their characteristics is also interesting. So here it is delta R by R. This is your epsilon, and you can measure both the positive strain and negative strain. That means it could be under tension or it could be under compression. So the semiconductor type strain gauge will have two types of characteristics. This we'll call it a P type, where the resistance increases with area with strain, and this is your N type. The resistance decreases with strain, and what we can say, and this is your operating zone. What do you mean by operating zone? In this zone, the characteristics of the strain gauge is more or less linear, but beyond it, it is highly nonlinear. So in these cases, you can have a gauge factor of 100 and 150 to 150, and this can be also, so it is a gauge factor is positive, and here the gauge factor is negative. We can have both the semiconductor and area. Okay. So these are the, so we can conclude that the strain gauge and have a two types, the metal type and the semiconductor type. But as I told, the semiconductor sensitivity is high, but the major issue is obviously that it's the non-linearity is a major issue. And normally the specifications, so this typical strain gauge specifications, okay, one is we know the R is equal to, say it is 120 ohm. I just say one example. As I told that it can be 120 ohm, 150 ohm, uh, yeah, 350 ohm or like this. Yeah. So this means that edge factor, say it is 2.0. Here we call it unstrained resistance. It is 120 ohm plus minus 1 ohm. So there is a variation, but was we manufacture it, there would be some variation. So it can, they say that the company says that, okay, it will not go beyond 1 ohm resistance variation. And linearity is plus minus 0.3%. Then maximum gauge current is 15 milliampere to 100 milliampere, depending upon the construction or the, uh, we can say area. I just put it like that. Means, what do you mean by area? We have a strain gauge. Say, suppose we have a cantilever beam. I will just show you a cantilever beam. This is a strain gauge here. I put it here. So the point is that what if this current I can go from 15 milliampere to 100 milliampere. This depends upon also the heat dissipation area here, where it will be, and also how good is the heat dissipation and all the things. So naturally we will have to look into, because the what is the heat dissipation, whether the current has to be carefully looked into, that it doesn't go beyond this one. Otherwise what will happen, there would be a heat generating there, and that may change again the resistance and also some more problems. So always say that what is the current rating is important, and always better to have go to the lower go work beyond the lower current rating of this one. And obviously maximum temperature, it is say 150 degrees, because the strain gauge is glued. We'll come to that one. The strain gauge is glued to the structure. So if it is, the temperature goes high, so naturally what will happen, that glue may loosen it, and so naturally the strain may not be able to be, be transmitted to the strain gauge properly. So this is important. The glue may, the characteristics may change. So it is all here, obviously it is better to operate it on this one. But I am telling a typical structure, I mean specifications we look for, and these are the things I can just tell it like this. So next will be definitely what will be the construction of the strain gauge. So the construction of the strain gauge, how we fabricate it, how you place it, how do the things there. And definitely these are very important. The fabrication, we should know the process, at least have some idea, and also to put it on your case. So you must be very careful in placing the strain gauge at proper place or like this. Otherwise, there would be some error in measurement. So if we look at it broadly, because the strain gauge is used for different types of there. It may be for measurement of very small pressure variation, pressure variation or small strain variation. Or also it could be of very large building structures. Say suppose we want to measure the tilt of the large building structure. We often also use the strain gauge for measuring. So it has got many applications. So it could be a large building and bridges and etc. Also they are used, or it may be a very maybe a pressure gauge for measurement of your cuff pressure, or maybe very small size or like this. So for this one we can have typically two types. One is unbonded, another is bonded. So what is unbonded? We'll come to it afterwards, but let me tell you right now, strain gauges are not normally used in single piece. They are used two or four or like this together. So this unbonded one is used for measurement of strain or displacement of big structures and etc. So what we have is some things like this. Say suppose this one is a fixed structure, and this one is a moving structure which can move it. Basically, you can say, as I have told, that the A between two buildings, you can say the structure is two buildings are like this. And what we do is that among these two buildings, we nail and fix simply this sort of strain gauge wires in between. Similarly, one between the fixed structure and one between and another one in the moving structure. So what we can see is that if it, so let us call it a 1, 2, 3 and 4. So if the moving structure moves towards right, then what will happen? 2 and 4 will be under, 2 and 3 will be under tension, while 1 and 4 will be under compression. So what we do is that in between these two structures are like this. So we can have, you can get some wires, nail these wires and connect the buildings or big structures are like this, and we can. So this is called the unbonded because we don't have to fix it online. So it is basically simple wires are read. But most of the cases we have it, that strain gauges are fabricated fast, and They are simply bonded or glued over the surface of the test bench or test structure are like this. So, so what we can say, the other one is called the bonded, and for this one we can say simply the bonded metal. Simply a bonded metal where is that we have some sort of backing material where over where the strain gauge is placed, and simply we can say that simple wear, strain gauge wear are fixed there. Strain gauge wears, very fine and thin wear, they are fixed like this there. So, this is called the bonded metal wear. But these wears are very thin and there, and one more problem is that we normally try to measure the strain in one direction. So, if it is in one direction, so what will happen? This once this whole backing material, I will come to the backing material, and there is glued uh, over the surface using the there epoxy or something there. So that the strain of the structure is transferred to this one there. So it measures in one direction, but you can see that these sides and these sides on the top of it, so what will happen, they will measure the uh, strain in the x direction also, which is not really advisable. And also this handling these wears and connecting wear, lead wear with it for this metal wear is really difficult. So on the other hand, what we have is that more practical, what we have the strain gauges in the market, they call it, what we have it is a metal foil type. So metal foils, they can be fabricated in bulk, and they are fabricated using photolithography technique. I think you know the photolithographic technique that is used for semiconductor, I mean transistors and all other things here. So what we have, what some backing material, what some substrate, you put some there, say metal or like this there, and then you put some mask over there to generate some pattern, and cover the mask with this one with the mask there, and remove the unmasked portion by some etching or techniques like this, and generate a pattern there. So the advantage is that you can have a very precise control and bulk fabrication and all other. So here also with the backing material, what we have it in this case, because suppose we want it, the strain should measure in these zone itself. The strain it should measure in this zone there. So what we do is that These are the connecting leads where we have it. This is a metal, or metal means strain gauge material, or strain gauge metal. I just connect it like this. Similarly, so these lead wires are like this, which is taking the connections. So they are quite thick. So naturally, they do not contribute to the change in resistance there. So the active area is where we have very thin line there. And then again the connections here, and then again another one like this, then again another one like this, and then connected. So what will happen is that, and obviously we will have to take the lead wires. So these are there. So these are where the strain gauge materials have been deposited. Uh, they have been deposited. They are put in pattern properly using a photolithographic technique there, and that is and over a backing material of the substrate. I am not showing you, but you can also see any, just you say, I mean, in the net, you just see what is strain gauge, how does it look like. These figures and diagrams, they are more nice, and the dimensions, you can have it and have the idea nicely. So, just I am trying to give you some basic idea there. So, we can have a bonded metal wire type or bonded metal foil type. So, the bonded means, so this strain gauge is available and overall dimensions may be 2 millimeter by 2 millimeter. I am just giving an idea, 2 millimeter by 2 millimeter, very small size. You can show that it can measure the strain at a point in a particular direction. So, you can see it will not, other directions, it will not measure the strain there. But only important thing, as I have told, that is the bonding material, I mean the backing material. So the choice of backing material and the bonding materials, these are also important. And another is, this is also important. The backing material means, okay, what is the backing material here? This is the backing, wherever the strain gauge is fabricated or like this here. So one more important point of this, so they are called it normally, it is impregnated phenolic impregnated paper. So it is phenolic impregnated paper. That means some sort of oil or like this that is dipped, the paper is dipped into this one, and that is called the phenolic impregnated paper there. And this one, the idea is that phenolic impregnated paper, this if we just put it there, important thing that it will not be hygroscopic, because if it is hygroscopic, the paper will absorb moisture and again generate some strain again. So some strain will be generated due to the if it is the absorption of water, but that is will not happen if it is an phenolic impregnated paper tier. And this one, as I have told you, that this is a 2 by 2 millimeter type of strain, typical value or like this there, that has to be bonded over the structure, maybe a steel structure, maybe some other structure. But important thing that the strain has to be carefully, the outside the structural strain has to be transmitted, faithfully transmitted to the strain gauge, because if they are not so, it has to be very tightly glued over the structure there. If it is not, then definitely it will cause some problem. And similarly, the bonding material also, if it generates some strain, that will also cause some problem. So these bonding material are basically, we call it, they are epoxy uh, cellulose. So these are the materials normally, etc., used for this one. But definitely it has to be looked into, and we need to uh, note down that this bonding material, there has to be fabrications or the bonding has to be done carefully. Otherwise, even if your structure, strain gauge circuit or everything is fine, but if it is not bonded, the strain gauge is not bonded properly over the structure, that will cause the problem. Lastly, what I wanted to say, another term and introduce another term, that is called the rosette. Strain gauge rosettes. What is rosette? So as I have told, that this strain gauge, it can measure the strain in one direction. But often we want to measure simultaneously strain at a point in different directions. In that case, what we call it, we use a strain gauge rosettes. It's nothing but we put an identical structure or like this there, but over it, but rotate it by 90 degrees. Then it will also have another one which will have which can measure strain in 90-degree area. So what we can just we can schematically we can show that, okay, this is your strain gauge for the measurement of in the wide strain in y direction, but another one over it we can have a strain measurement in the x direction. And so this is 1, 1 dash, 2, 2 dash, and we can have another one also at 45 degree and say 3, 3 dash. Say this is 45 degree. So we can measure at this point the three strains, strains in three direction, in x direction, y direction, and in between 45 degree. So there are several different types of structures are there, rosettes are there, where there are certain diaphragm type rosettes are also there. We will discuss it afterwards in this strain gauge. So let us conclude. We have introduced the strain gauges and we have seen the how the strain gauge works and what is the basic relationship. We have introduced the gauge factor, what are the materials we have it, and the how they are fabricated, and finally how they are connected and used there. So with this, I conclude today's here. So the signal conditioning circuit would be discussed in the next class. Thank you.